Thanks, Nick. First, I'd like to start off with saying Happy International Moon Day. Today's July 20th, the 53rd anniversary of the Apollo 11 moon landing. So let me jump right in. So here I'll show how we use lunar regolith simulant to develop correlations between cone penetrometer measurements and regolith density. And we were also able to replicate the geotechnical characteristics of the Highlands regolith as measured in situ during the Apollo 16 mission. And so I always like to start off with why do we care? And so upcoming robotic and human missions to the moon will begin the process of establishing infrastructure for a long-term lunar presence. And as we all know, NASA plans to achieve this at Highland landing sites at the South Pole. Long-duration stays will require a firm understanding of the geotechnical characteristics of the near-surface regolith column, which would be important for infrastructure development and other mission logistics. And of course, regolith samples brought back from Apollo are much too precious for large-scale engineering tests, so we need to use lunar simulants. And so here's an anecdote that I think really nicely emphasizes the overall objective and purpose of this study. Shortly after the Apollo 11 mission, NASA technicians had Buzz Aldrin walk on a simulated lunar surface, which was sand about 15 centimeters deep, of course with 5/6 of his weight supported in a marionette rig. And when asked how the test track compared to walking on the actual lunar surface, Aldrin replied that the sand was too yielding. While walking on the moon, he noticed that although the regolith was soft at the surface, there was a firmer stratum underneath. So simply put, for Earth-based engineering tests, simulant should be packed in layers of specific densities rather than just dumping it into the test bin. So to understand how the regolith will withstand construction activities, it will be critical to replicate the geotechnical properties and the regolith density profile while performing Earth-based testing. And here we'll use the Apollo 16 landing site as a Highlands analog to guide our Earth-based engineering tests, which in turn will help inform future lunar exploration at the South Pole. So the first step in this type of work is to understand the geotechnical properties of your simulant. And we've done this for Exolith Labs LHS-1 Highlands regolith simulant. And if you're interested, I'll direct you to Longfox et al. That's in the audience right now. In this year's ASCE Earth and Space proceedings. So specific gravity, density, shear strength values for LHS-1 are all in good agreement with those found for the lunar regolith during the Apollo missions. And at right, I show the relationship between dried LHS-1, the relationship between bulk density and relative density, and parameters which are important for our testing. So for the cone penetrometer measurements, we used a RIMIC CP40 cone penetrometer to obtain penetration resistance values, and that's measured as stress in kilopascals versus depth for LHS-1, packed at various densities in clear acrylic test bins. And on the right, you can see our raw data, and that's the colored curves there, for 5 CPT insertions into LHS-1, which we packed at 76% relative density. We use these data to derive the slope parameter G, which is simply the stress over depth for these curves. And G is important for our correlations, as I'll show very shortly. Here's CPT data from Apollo 16. And although CPT data and also core tube data indicated that the regolith stratigraphy varies on a local scale at the Apollo 16 site, readings from Station 4 and Station 10 display a general similarity, and that a firm layer is encountered at about 5 to 10 centimeters below the surface. Then resistance increases significantly, which indicates a denser, stronger regolith layer at around 15 to 20 centimeters below the surface. This interpretation is reinforced by blast effects from the Apollo 16 LM. Although the descent engine nozzle, as you can see, rests only centimeters above the surface, no blast crater was produced. So apparently the upper regolith layer was blown away, leaving the denser lower layer exposed. And here's Charlie Duke performing CPT measurements during Apollo 16. And he ran into a little trouble here, and hopefully that won't be me when I'm running experiments in the lab. So the use of in situ lunar geotechnical data to guide Earth-based testing, which in turn can inform future lunar exploration, is, I think, a very nice example of the survey mantra that exploration enables science and science enables exploration. So we took a total of 50 CPT measurements, and we did 5 insertions each at 10 different density packings to determine the range of strength in terms of G for LHS1 over a range of density from 53% to 94%. And these data yield a strong exponential relationship and are in good agreement with the range of G values estimated during the Apollo 16 at stations 4 and 10. We also created simulated 2-layer stratigraphic profiles using LHS1 in our test bins. In test 1, we packed LHS1 to relative densities of 72% for the upper layer and 94% for the lower layer. Our data, which is the blue curve, let's see, the blue curve there, is then adjusted for lunar conditions. And interestingly, the reduction factor is not 1/6. It turns out to be about 0.3, which is the black curve. And we then compare that black curve to those measured in situ during Apollo 16, which are the gray dashed and dotted curves. And you can see that we did a good job of replicating the properties of the lower layer, but we undershot the resistance values for the upper layer. In test 2, we packed LHS1 to relative densities of 90% for the upper layer and 95% for the lower layer. And we show the same curves here as for the previous slide, and you can see that we did a much better job of matching the upper layer and also replicating the overall stratigraphy from the Apollo 16 landing site. And to stay on time here, I've got, here's my summary slide, and I will leave my summary points there while I talk about some applications from this type of work. And so data from these type of experiments could help plan the construction of roadways and launch landing pads by using controlled rocket exhaust to remove the less dense superficial layer while leaving the lower, denser layer exposed, which then could be stabilized. And so I've also got a shameless plug. We're working with Exolith Lab to develop Rider, which is a single wheel test rig, where we'll expand upon this work to explore questions regarding trafficability. And so see Conway et al., abstract and poster at this conference. And I believe I made it through an entire lunar presentation without once saying the word sustainable. And with that, I thank you for your attention, and I'll take any questions. Oh yeah.
Sorry about that.
Yeah. I could be, well, in the time I could show if you're, and I left the table out of my slides. I always try to do that. So there's geotechnical properties. This is from Long Fox et al., as I said, in this year's ASCE, Earth and Space. And we tested undried and dried, and then the lunar regolith values from, I don't have the, a lot of these references are from Carrier et al., Lunar Source Book, Mitchell et al., it's 1972, Apollo 16 Preliminary Science Report. So if you're interested in seeing that. Another thing I could show is here, another CPT insertion data. I showed station 10 during the presentation. Here's data from station 4, and you can see it, the same general. Now at the Apollo 16 landing site, they showed that the regolith stratigraphy is variable on a local scale, but the general similarity being at 5 or so centimeters below the surface, you got a firm layer, and then resistance increases, indicating a denser layer underneath. And then, interestingly, on this one, it really goes down after that second layer. The resistance went down, so maybe there's a softer layer underneath that even. Nick, are we at 10? Okay, yep. Thank you very much.